Good day, students. So welcome to part 4 of the AP Calculus AB 1998 multiple choice review questions. In this review installment, we're going to be going over questions 16 through 20. All right, so let's take a look at question number 16. So in question 16, we're asked to find f prime of x when f of x is sine of e to the negative x. All right, so this is a test on your understanding of the chain rule and composition of functions. In this function right here, we have a composition of 3 functions. So we're going to apply the chain rule starting from the outermost function all the way to the innermost function, all right? So let me break down the functions for you. I'm going to call them functions h, g, h, and k. So f of x, so let me just state what they are first. So function g of x is the outermost one, which is sine x. Okay, and then h of x is the next one, which is e to the x, and then k of x is negative x. Okay, so f of x is basically the composition of these 3 functions. It is g of h of k of x. If you compose those 3 functions, let's see. If you compose those 3 functions, what you have is sine of e to the, change color to blue, e to the negative x. Okay, so you see the composition of 3 functions here. So when we're using the chain rule, we're going to start from the outermost function, and then we're going to differentiate the outermost function, keeping the inner 2 fixed, and then we're going to shift to the second function on the inside, keeping the innermost one fixed, and then we'll differentiate the innermost function. Okay, so that's basically how you differentiate it. So let's say you have g of h of k of x. So let's say you wanted to do g of h of k of x prime. How do you differentiate this? So the chain rule just basically says you start from the outermost one, g, holding h of k of x fixed, and then you multiply that by the derivative of h of k of x, holding the innermost one fixed, and then you basically multiply that by k prime of x. So start from the outer way all the way to the innermost function. So that's basically what the chain rule is, all right? So let's apply that to this problem. F of x is going to be, I'm going to do it step by step, okay? F of x is sine of e to the negative x. So that means f prime of x is going to be, let's start with the outermost one. The derivative of sine is cosine, right? So it's going to be cosine. When I differentiate that to keep the 2 inner composed functions fixed, so e to the negative x fixed, times the derivative of the innermost function, so e to the negative x prime. I'm going to use prime notation. I can call it d dx of this, same thing, okay? And then that equals cosine e to the negative x. Now we're differentiating the inner function, but the inner function is also a composite function, okay? So we're going to differentiate the exponential first. So the derivative of e to the x is just e to the x, so it's e to the negative x, times the derivative of the inner function, which is negative x prime, okay? So we've done g prime of x here, and then now we did h prime of x. Now to do k prime, which is the innermost one, we're going to use the power rule, e to the negative x times e to the negative x times the derivative of x to the 1 is just negative 1, so it's going to be negative 1. All right? Okay, so let's just rewrite this. If we write it properly, it's going to be negative e to the negative x cosine e to the negative x in parentheses like that. All right? So we can clearly see that the answer is option letter E. Okay, let's move on to question 17. So question 17 just tests basically our understanding of the relationship between f and f prime, and then f and f double prime. All right, so let's take a look at this function. If you just look at this function, we can immediately tell what f of 1 is. Okay, because in this problem we need to compare f1 with f prime of 1 and f double prime of 1. So we can see in this function that f of 1 is equal to 0. Okay, because when you input 1, you get output of 0. All right, so we have this down. Now, before I tell you the behavior of f prime and f double prime, let's do a real quick review on the relationship between f and f prime and then f and f double prime. So if f is increasing, okay, is going up, if f is increasing, what does that tell us about f prime? If f is increasing, they have a positive slope. That means f prime is positive, or we can say it's greater than 0. All right. If the function is decreasing, or going down, what does that tell us about f prime? Well, that tells us that the slope is going to be negative, right? So f prime is going to be negative or less than 0. Okay, so this is the connection between f and f prime. How about f and f double prime? Well, what is the connection between f and f double prime? Well, let's review that real quick. If f is concave up, okay, if f is concave up, then f double prime is going to be positive, positive or greater than 0. Okay, and if f is concave down, basically the concavity is downwards, then f double prime is going to be negative or less than 0. All right, so at the point at x equals 1, at x equals 1, what do we know about f prime? The function is going up, it's increasing, right? F prime, uh, um, or what do we know about f? Uh, f is increasing, is going up. So if f is increasing, then we know that f prime has to be, f prime of 1 has to be greater than 0. Okay? And then what do we know about the concavity? At x equals 1, see how it's curving downwards? The concavity is facing downwards, so f is concave down. So since it's concave down, look at the word down means negative. That means f double prime at 1 is going to be less than 0. Okay? So we see that we see how the three compare with themselves, right? So we know that f double prime is negative, so it's going to be less than f1, which is 0, and f1 is going to be less than f prime of 1, which is positive. Okay? Hopefully this expression makes sense. So let me use a number line just to reiterate what I just said. So at 0, we have f. Okay? And then over here we have f double prime because it's negative. Okay? Because it's negative. And then over here we have f prime because it is positive. Okay? So this is f's territory. And then this open circle here, any number, a positive number will satisfy f prime because it's positive. And then this region less than 0, this is where f double prime resides. So using the ordering of numbers in the number line, we can see that this f double prime is less than f, and f is less than f prime. All right, so the answer, let's see, is option letter D. All right, so our answer is D for this one. Okay, let's move on to number 18. It says an equation of a line tangent to the graph y equals x plus cosine x at the point 0, 1 is. So remember in algebra, the equation of a line, point slope form is y minus y1 equals m x minus x1. So we know that x1 is 0 and y1 is 1. So all we need is m, okay? So m is question mark. So we have only a point. The beauty of derivatives is that we can use that to find the slope of a line with just one point. We don't need 2 points as in algebra 1 and 2, okay? So how do we do that? We just find the derivative of this point at the specified x value. So m is basically dy dx at x equals 0. Okay, so let's find what the derivative is first and then evaluate it at x equals 0. That will give us a slope. We'll plug in this equation and that will give us our equation. All right, so dy dx is the derivative of this function. Differentiate this term by term. Derivative of x is 1. Derivative of cosine is negative sine x. Okay, so the slope when x is 0 which is basically the m, is 1 minus sine of 0. We know sine of 0 is 0, so that is equal to 1, and that is the value of m. So basically we have all the information we need. M is 1, so let's write down the equation of our line in points slope form. Y minus 1 equals m, which is 1 times x minus 0. So I just plugged in 1, 2, 3 into this equation right here, and that's how I got this, okay? All right, so let's simplify this since our answers are in slope intercept form. So we have y minus 1 equals x. If you subtract 1 from both, add 1 to both sides, you have y equals x plus 1. And the final answer for number 18 is option letter B. All right, let's move on to question number 19. In question 19, in 19, we are supposed to considering this function, then where does f have inflection points? Okay, so f double prime of x is given by x times x plus 1 times x minus 2 squared. So you have points of inflection when f double prime changes from positive to negative, okay? So that's when f has points of inflection, when f double prime changes sign. So what we're going to do is create an interval and then select appropriate test values within each uh, point, and then that will help us find the inflection point. So in order for x to change sign from positive to negative, it must hit 0 first. So what values is it neutral, neither positive nor negative? We have to find those and then create intervals around those points. Okay, so we set each of these to 0. So we have x equals 0, and then x plus 1 equals 0, and then x minus 2 equals 0. All right, set each of the roots to 0. This technically is x minus 2 squared. But if we solve this, it's going to be the same thing. So this is already solved. We solve this, we get x equals negative 1. And then if we solve this, we root both sides. We'll have x minus 2 equals 0. We add 2 to both sides, we have x equals 2. Okay, so these are the points where the function has a switching concavity. Okay, there might or might not be a switching concavity. So at these points, it's neither concave up nor concave down. So that's the deal there. Okay. All right. So let's make our number line. Okay, I'm gonna graph the points where the function is neither concave up nor concave down. So we have negative 1, 0. I'm not doing this to scale. Okay, so pardon me, and then they call this 2. Okay, so let's label the intervals. This is what I care about. What's happening with the signs in between these intervals, okay? So let's call this interval 1, interval 2, interval 3, and interval 4. All right? So all I care about is the sign. Okay, the sign of the second derivative on each interval. So whenever there's a sign change, we know that the point where the sign change happens is a point of inflection, okay? All right, so we're going to pick our test values for interval 1. We're going to test x equals, pick a number to the left of negative 1 on the number line. How about we use negative 2? And then we're going to be plugging it into the function x times x plus 1 times x minus 2 squared. This is what we're going to be plugging them into, okay? All right, so I'm testing this, so I'll just plug in negative 2. So I have negative 2 times negative 2 plus 1 times negative 2 minus 2 squared. All I care about is the sign, okay? So I just want to know the sign of these three quantities to determine the final sign. So this is already negative, it's going to be negative. This minus 2 plus 1 is going to be a negative number because the negative number is bigger. Where did I put negative 1? It's negative 1, but you don't need to do it. You just need to focus on the sign, okay? So this is also negative. Now, this last quantity will always be positive because if you square a positive and a negative number, you always get a positive number, okay? So this is going to be positive. All right, so when you multiply negative times positive, you have positive. So on this interval, uh, um, the second derivative is positive, which means the function is concave up. All right, interval 2, what are we going to test? Let's test a number between negative 1 and 0. We can test negative 1/2. Plug it into this function, the function for the second derivative. Let me organize this a little bit nicer so you can see what I'm doing. So this is our test function right here. And then these are test values. I did the first one, and I'm going to do the next one, okay? Okay, now let's plug in negative 1/2. Remember, all we care about is the sign, okay? What's the sign of each quantity and the final sign after multiplying the signs of each quantity. So plug it into that function. We're going to have negative 1/2 times negative 1/2 plus 1 times negative 1/2 minus 2 squared. Okay, this is going to be negative. This piece, the smaller number is negative, so this will be positive. And then this one is always positive because you're squaring it. This square makes it positive, all right? So minus times plus is going to be minus, all right? So that means on interval 2, the second derivative is negative. The second derivative is negative, and that means that my function is concave down. Wow, there's a switch here, point of inflection right here. Okay, let's move on to the next one, interval 3. Two more to test, and then we can determine where our points of inflection are. So interval 3, we're going to test, what are we testing? A number between 0 and 2. Easiest one is 1. Plug that into the function, the second derivative function. 1 times 1 plus 1 times 1 minus 2 quantity square. This is positive. 1 plus 1 is positive. 1 minus 2 is negative. 1 squared is positive also. When we multiply all this positivity, we get positive, okay? All right, interval number 4. Well, this interval 3 is positive. A function is concave up. See another point of inflection here. And then the last interval we're testing is interval 4 when x is bigger than 2. What are we going to test? What is a good number to pick? Well, how about we work with 4? Just to match this 4. It doesn't even matter what you pick. As long as it's bigger than 2, you're fine. Anyway, so we're going to be testing x equals 4. We just plug it into the second derivative function and see what the sign is. Okay, so we have 4 times 4 plus 1 times 4 minus 2 quantity square. This is positive. 4 plus 1 is positive. 4 minus 1 squared is positive. Positive times positive times positive is positive. Interval 4 is positive, hence it is concave up. Okay, so at what points was there a switch in concavity or a switch in the sign of the second derivative? At negative 1 and at 0. Okay, so point 2 is not a point of inflection because it was positive before and after that point of around that point, so it's not a point of inflection. So our only points of inflection are x equals what did I forgot already? X equals negative 1 and x equals 0. Okay. All right. Now let's move on to the next number, number 20. Number 20, we asked the final values of k for which this definite integral, negative 3 to k, of x squared dx is equal to 0. All right. Okay. So when we do this, basically we end up with an equation, polynomial equation after integrating, and then we'll solve that. All right. So let's go ahead and integrate this using the uh, techniques of integration. We're going to be applying FTC part 2 afterwards. Okay, so using the power rule for integrals, the antiderivative of x squared is x to the third over 3. We're going to be evaluating this from negative 3 all the way to k, and then we're going to be setting it equal to 0 and then solving it. Okay. Okay, so using FTC part 2, plugging the upper limit, we have k to the third over 3 minus, we plug in the lower limit, negative 3 to the third over 3 equals 0. So we have k to the third minus 3 cubed is a negative 27. So negative 27 plus negative 27 times a minus is plus, right? Plus 27 over 3. All right. So we need to solve this equation right here. So multiply both sides by 3. We have k to the third plus 27 equals 0. K to the third has to be equal to negative 27. And then you basically take the cube root of both sides. And then you have k equals negative 3. So that goes your final answer. Option letter A. So A is our final result. All right, so there you have it. Thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here. And then please post the comments to let me know what you think about this presentation, or click like if you liked it, or please come and find me at mattlister.com. Thanks again and have a wonderful day.